Good day, everyone. Today we are going to discuss an open channel. An open channel is a type of fluid conduit with a free surface open to the atmosphere, such as rivers, canals, and drainage ditches. Its importance lies in its use for efficient water conveyance in irrigation, drainage, flood control, and hydroelectric power generation. Open channels are essential in managing water resources and infrastructure, facilitating the movement and distribution of water in various applications. We have a sample problem here involves calculating the discharge in a natural channel during a flood stage, which includes a deep main channel and two floodplains. For the deep channel, we have given data of depth of Y sub 1, which is 20 feet, width of B sub 1, 40 feet, and a Manning's roughness coefficient of 0.020. And for the floodplains, we have depth of 5 feet, width of 100 feet each, a Manning's roughness coefficient of 0.040, and slope channel of 0.0002. To calculate the discharge for the deep channel using Manning's equation, knowing that Manning's equation for discharge is 1.486 over n AR raised to 2/3 S raised to 1/2, where n is Manning's roughness coefficient, A is the cross-sectional area of the flow, R is the hydraulic radius. To solve hydraulic radius is cross-sectional area of flow over wetted perimeter, which is the length of the channel boundary that is in contact with the water, and S is the slope of the energy grade line. For a rectangular section, the cross-sectional area is given by area is equals to B multiplied by Y, where B is the width of the channel and Y is the depth of the flow. The depth of a flow is 25 feet, the Y sub 1 plus Y sub 2. Multiply with the width of the channel, which is 40 feet, resulted to 1,000 feet squared. Next is we need to solve the wetted perimeter that needed in getting the hydraulic radius. The formula getting wetted perimeter is B sub 1 plus 2Y sub 1, where B is the bottom width of the channel, the horizontal contact with water, and 2Y sub 1 is the sum of the two vertical sides of the channel, where each side contributing Y sub 1 to the wetted perimeter. As we plug in the data in the formula, where B sub 1 is 40 feet, plus 2Y sub 1, where Y sub 1 is 20 feet, the result is 80 feet. Now that we have the value of the cross-sectional area and the wetted perimeter, we can now solve the hydraulic radius that is also required in Manning's equation. The formula of hydraulic radius is cross-sectional area over the wetted perimeter. 1,000 feet squared over the wetted perimeter, which is 80, the hydraulic radius is 12.5 feet. Now that we have the unknowns, we can now substitute it into Manning's equation. Manning equation is 1.486 over n, where n is 0.020, and the area of 1,000 feet multiply the hydraulic radius of 12.5 raised to 2/3 and slope of 0.0002 raised to 1/2. If we compute, the discharge is 5,659.5 cubic feet per second. Next is to calculate the discharge for the floodplains. Since there are two identical floodplains, the discharge for each floodplains is calculated and then doubled. To get the discharge, we also need the area, wetted perimeter, and the hydraulic radius. We are going to solve for each floodplain. Since area is the depth of the flow, which is the Y sub 2, multiply with the width of the channel, the B sub 2. So area is 5 feet multiplied by the width of the channel, which is 100 feet, resulted to 500 feet squared. Next is the wetted perimeter. Using the formula, we can plug in the data where B sub 2 is 100 feet plus y sub 2, where y sub 2 is 5 feet. If we add this, the result is 105 feet. And for the hydraulic radius, it is cross-sectional area over the weighted perimeter, so 500 feet squared over 105 feet. The result of the hydraulic radius is 4.76 feet. Now substituting it into Manning's equation for one floodplain. For Q sub 2 equals to 1.486 over Manning coefficient of 0.040, multiply the area of 500 feet, the hydraulic radius of 4.76 feet raised to 2/3, and slope of 0.0002 raised to 1/2. The result for the discharge in one floodplain is 743.33 cubic feet per second. Since there are two floodplains, we are going to multiply 2 to the discharge in one floodplain. The result of multiplying 2 to 743.33 is 1,486.66 cubic feet per second. Since we are finding the total discharge and knowing that the total discharge is the sum of discharges from the deep channel and both floodplains. The discharge of the deep channel is 5,659.5 cubic feet per second, and the discharge in both floodplain is 1,486.66 cubic feet per second. And if we add these discharges, the total discharge is 7,146.16 cubic feet per second.